All right, let's take a few minutes now to work through some of the complex functions in MATLAB. These are the ones we saw on the board in the last video. Let's start with an exponential function. Just simply, can you jam a complex number into the exponential? That is, can you raise e to the I power? Well, in concept, sure. E is a number, I is a number. I should be able to raise one number to the other one. And of course, there it is. Now, would you expect that to be the answer? Probably not. I wouldn't. Well, hang on a second. If e to the ix equals cosine x plus I sine x, just like the Euler relation says, let's try this. X is 1 here. Cosine's 1 plus I times sine 1. Do I get that same number? Booyah, there it is, right there. So that works fine. And of course, I can try this with any number I like. Can I do that? Sure. So remember, complex numbers are still just numbers, whatever other properties they may have, and e, whatever other properties it might have, is also just a number. So I can raise any e into any complex power I want, and it'll still work. It's just basic mathematics. I'm going to clear the command window here. Let's clear the workspace as well. And let's go into polar coordinates. Now, if I assign z1 to a number we used before, you can see I've got the command history over here, so I'm just pulling all this stuff back up. And I say z2 is that other number we worked with before. Got them. You can see them right there in the workspace, so they exist. Well, just for completeness, let's say z is z1 times z2. I do want an answer, so I'm not going to put the semicolon at the end. And there's 3 plus 1i. We've seen that before. Well, could we do this in polar coordinates? Sure. So let's call r1 is the absolute value of z1. Now I could say this. I could say that it's the square root of 1 squared plus 1. This is kind of silly, but I could do that. Well, let's try something else here. Rather than that, let's just say it's the absolute value of z1. Now, the nice part about MATLAB here is it's completely happy with complex numbers. It'll give me the same answer, and there it is. So I'll say r2 is the absolute value of z2. Unfortunately, that's the number we saw on the board before. I did get it right. Next thing I need are some angles. Well, let's see. The angle of the first number, let's call it angle 1, I guess, is now it's the arctangent of the imaginary part over the real part. Because remember, the imaginary part is vertical, the real part is horizontal. So the arctangent of that is the angle. So I just say a tan, imaginary part of z1 divided by the real part of z1. And so I get that number back. That's the one we saw before. Let's try that for 2. Now I'm going to cheat here. I'm just going to edit the previous command. There, saw that before as well. So let's multiply those together. Let's say r equals r1 times r2. Okay, saw that before. And angle equals angle 1 plus angle 2. And again, saw that before. Now, how am I going to turn that into a plus bi? Well, let's just say a equals r times cosine angl, angl. Ooh, look at that, 3. b equals r times sine angle, angle, there we go, 1. Okay, so a plus I times b is 3 plus 1, just what we had before, just what z was before, and you can see it right there. All right, so that totally worked. Let's clear the screen here. We're not going to clear workspace because I do actually need some of those numbers. Let's say that I want to divide. If I want to say z1 divided by z2, all right, got that before. Let's say now r equals r1 divided by r2. And angle equals angle 1 minus angle 2, and say A equals, all right, that ought to work. Oh, look at that. Man, don't you love it when a plan comes together? And there it is. So A plus IB is 0.2 plus 0.6i, just like it was when we said Z1 divided by Z2. Got the same answer. So there you go. Like I said, in MATLAB, this is really pretty straightforward, but it's hopefully helpful to see this all typed out. Well, I hope this helps, and we'll talk to you next time.